Titanium is one of the most valuable engineering metals on Earth. Incredibly strong for its weight, highly resistant to corrosion, and able to survive extreme heat and stress. Yet most people never realize how difficult it is to produce. Unlike common metals like iron or aluminum, titanium is not easily extracted from ore and cannot simply be melted in a basic furnace without reacting violently with oxygen and nitrogen. Producing aerospace-grade titanium requires advanced chemistry, extreme temperature control, vacuum environments, and a manufacturing chain so demanding that only a small number of facilities worldwide can do it consistently. And today on the How Factory, we're going deep inside the titanium production process to see exactly how titanium is made. From raw ore to aerospace-grade metal used in aircraft, spacecraft, and high-performance machines. Titanium was discovered in the late 18th century, but for more than 100 years it remained a scientific curiosity because no one could produce it in useful quantities. The challenge wasn't finding titanium, it's abundant in Earth's crust. The challenge was isolating it. Titanium bonds strongly to oxygen, and when heated it reacts aggressively with air. It wasn't until the 20th century, with breakthroughs in chemical reduction and vacuum metallurgy, that titanium became practical. Once engineers realized titanium's strength-to-weight ratio and corrosion resistance, it became a strategic metal for jet engines, submarines, and spacecraft, and modern industry has been scaling up ever since. The journey begins with raw titanium ore. The most common ores are ilmenite and rutile, mined in several regions worldwide. These minerals contain titanium bound to oxygen and other elements. Ore is extracted using surface mining methods, then crushed and processed to concentrate the titanium-bearing material. Because titanium is used in high-performance applications, purity begins at the mine. Concentration plants use gravity separation, magnetic separation, and flotation methods to remove unwanted minerals, producing a refined concentrate rich in titanium dioxide. For many industries, titanium dioxide itself is already valuable as a pigment used in paint, plastics, and paper. But for metal production, the concentrate must be converted into a form that can be chemically reduced. That conversion step is where titanium production becomes uniquely difficult. The next stage is chlorination. Titanium dioxide concentrate is mixed with carbon and fed into a high-temperature reactor where chlorine gas is introduced. Under extreme heat, the oxygen in titanium dioxide is removed, and titanium combines with chlorine to form titanium tetrachloride, a volatile liquid known as TiCl4. This chemical is the key intermediate for producing titanium metal. Titanium tetrachloride must be extremely pure because any impurities carried forward will weaken the final metal. TiCl4 is then purified through distillation. Because it has a relatively low boiling point compared to many impurities, distillation columns can separate it into high-purity titanium tetrachloride. This stage resembles chemical refining more than metal production, with sealed systems, corrosion-resistant piping, and strict moisture control. Titanium tetrachloride reacts violently with water, producing corrosive hydrochloric acid fumes, so every step is sealed and carefully monitored. Once purified, titanium tetrachloride enters the reduction stage, the heart of titanium metal production. Most titanium is produced using the Kroll process, developed in the mid-20th century and still dominant today. In the Kroll process, TiCl4 is reacted with molten magnesium inside a sealed reactor under an inert atmosphere. The magnesium strips chlorine away from titanium, leaving behind titanium metal in a porous, solid form called titanium sponge. This process happens at high temperatures and must be carefully controlled to prevent contamination. When the reaction is complete, the reactor contains titanium sponge mixed with magnesium chloride and leftover magnesium. The material must be processed further. The reactor is cooled and opened, and the sponge is removed. Because sponge structure can trap impurities, it is broken into pieces and cleaned. Next comes leaching and purification. The titanium sponge is treated to remove magnesium chloride and residual magnesium. This can involve vacuum distillation, where magnesium and magnesium chloride are evaporated away under reduced pressure, leaving pure titanium behind. The cleaned sponge is now a usable metal feedstock, but it is still not aerospace grade. That requires additional melting and refining. Titanium sponge is highly reactive when hot, so melting it is extremely challenging. Ordinary furnaces would contaminate titanium with oxygen, nitrogen, and carbon. That's why titanium is melted using vacuum or inert gas systems. The sponge is mixed with alloying elements depending on the final specification. For aerospace, the most famous alloy is Ti6Al4V, which contains aluminum and vanadium for increased strength and heat resistance. The sponge and alloying elements are compressed into large electrodes. These electrodes are then melted in vacuum arc remelting furnaces, known as VAR furnaces. In VAR, an electric arc forms between the electrode and a copper mold inside a vacuum chamber. The intense arc heat melts the titanium drop by drop, forming a solid ingot as it cools. The vacuum prevents contamination and allows gases to escape. Vacuum arc remelting is often performed multiple times. Aerospace-grade titanium may be double or triple melted to achieve extreme cleanliness and uniform composition. Each remelt reduces inclusions, removes trapped gases, and produces a more consistent microstructure. The result is a massive titanium ingot, often weighing several tons. Once ingots are produced, they enter forging and rolling. Titanium ingots are heated in controlled furnaces and forged using hydraulic presses that apply enormous force. Forging refines the grain structure, improving strength and toughness. Titanium forging requires careful temperature control. Too cold and it cracks, too hot, and the metal's properties degrade. After forging, titanium may be rolled into plate, bar, sheet, or billet depending on use. Heat treatment follows. Titanium's strength and ductility depend heavily on its microstructure, which is controlled by heating and cooling cycles. Heat treatments are performed in vacuum furnaces or inert atmospheres to avoid oxidation. For aerospace parts, even small property variations are unacceptable, so every batch is treated to exact specifications. Machining titanium is another challenge. Titanium is strong, tough, and a poor heat conductor, meaning cutting tools heat up quickly and wear out fast. Aerospace-grade titanium parts require advanced CNC machining, with specialized tooling, coolant systems, and slow cutting speeds to maintain accuracy. Titanium can be shaped into aircraft structural parts, engine components, fasteners, medical implants, and high-performance industrial systems. Quality control is relentless at every step. Titanium is inspected for chemical composition, oxygen content, grain structure, and mechanical strength. Ultrasonic testing detects internal flaws. X-ray and metallurgical analysis check for inclusions. Aerospace titanium must meet strict certification standards because failure is not an option. A microscopic defect could become catastrophic in flight. Sustainability also plays an increasing role. Titanium production is energy-intensive, especially during reduction and vacuum melting. Modern producers recycle titanium scrap from machining and manufacturing. Scrap can be reprocessed into new alloys, reducing the need for raw sponge and improving efficiency. However, contamination control remains critical, so recycling systems must be carefully managed. What makes titanium remarkable is that it is everywhere in the Earth's crust, yet extremely hard to extract into pure metal. Its production chain combines mining, chemical refining, high-temperature reduction, vacuum metallurgy, and precision forming. Titanium is not mass-produced like steel, it is engineered. From ore mined in the ground to titanium tetrachloride distilled in chemical plants, from sponge reduced in sealed reactors to vacuum-melted ingots and forged aerospace parts, the journey of titanium is one of the most demanding metallurgical processes on the planet. Every kilogram represents extreme control over chemistry and atmosphere. And that is exactly how titanium is mined, refined, reduced, purified, vacuum melted, forged, heat-treated, and shaped, transforming raw ore into aerospace-grade metal that powers jets, spacecraft, and advanced technology. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the materials, machines, and factories behind the world's strongest technologies.